Trying to lose weight? It's time to try Hers. At forhers.com/4u, you can access affordable, doctor-trusted weight loss treatments tailored just for you. These include oral medication kits or compounded GLP-1 injections. Through Hers, pricing for oral medication kits start at just $69 a month for a 10-month plan when paid in full upfront. No hidden fees, no membership fees. You shouldn't have to go out of your way to feel like yourself. Hers brings expert care straight to you with 100% online access to personalized treatment plans that put your goals first. Reach your weight loss goals with help through Hers. Get started at forhers.com/4u to access affordable, doctor-trusted weight loss plans. That's forhers.com/4u, forhers.com/4u. Paid for by Hims and Hers Health. Weight loss by Hers is not available everywhere. Compounded products are not FDA approved or verified for safety, effectiveness, or quality. Prescription required. Restrictions at forhers.com apply.
Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing bedtime astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
Welcome to the Deep Dive, where we plunge into the latest, most mind-bending research and bring you the aha moments that reshape how you see the universe. For you, someone who truly loves to connect the dots in cosmic evolution, imagine a universe that's barely a toddler, less than 1 billion years old. The vast, dark cosmos is just beginning to flicker with the first stars and galaxies. What colossal, powerful objects do you think were already out there, quietly or not so quietly, shaping its destiny? Was it a gentle, gradual unfolding or something far more, well, energetic than we ever dared to imagine? Today, we're not just talking about black holes, we're diving headfirst into the captivating subject of supermassive black holes, specifically as they blazed forth in the universe's infancy, a period astronomers lovingly call the cosmic dawn. These aren't the dormant, relatively serene giants we mostly see today. These were incredibly powerful, brilliantly luminous objects known as quasars. They were like cosmic lighthouses, shining across unimaginable distances, yet as we're about to discover, many were shrouded in a cloak of mystery. Our mission today is to explore an astonishing new discovery that is fundamentally reshaping our understanding of how truly common and influential these cosmic giants were in the universe's youth. It's a deep dive into sources that reveal a previously hidden population of these early behemoths, effectively doubling what we thought we knew. And all of it thanks to a remarkable combination of telescopic power that allowed us to peer through the cosmic fog. Get ready for some serious aha moments about the early universe you thought you knew, because it seems it was far more dynamic than we could have ever guessed. Okay, let's unpack this with our current understanding as a baseline. When we look at the universe today, it's become a pretty established fact that supermassive black holes are almost ubiquitous. Pretty much every large galaxy we observe, including our very own Milky Way, quietly harbors one of these monstrous objects right at its center. We're talking about masses that can reach millions, even billions of times that of our sun. They're just there, usually in a state of cosmic slumber.
Indeed. And they're mostly quiet now, right? It's just sort of sitting there. But what's truly fascinating here is how these cosmic engines influence structures on such massive scales, right down to the evolution of their host galaxies. While these giants are mostly dormant now, silently anchoring their galaxies, they become incredibly powerful when they're actively feeding on surrounding matter. This process is called accretion.
Like a cosmic whirlpool?
Sort of, yeah. Think of it like matter spiraling down a cosmic drain. As gas and dust get closer to the black hole, friction and immense gravitational forces heat it to millions, even billions of degrees. This creates a superheated accretion disk that blazes with light across the entire electromagnetic spectrum, from powerful radio waves to X-rays and gamma rays. This makes them incredibly luminous, bright enough to outshine the entire galaxy they reside in. This activity transforms them into quasars.
Right, the quasars. The really bright ones.
Exactly. And crucially, this intense radiation and the powerful outflows of gas it drives are believed to play a critical role in galactic evolution. It's thought to significantly affect the growth of its host galaxy by expelling gas, essentially clearing out the raw material needed for star formation.
So it stops stars from forming.
It can, yeah. This feedback mechanism is how we believe these cosmic giants have shaped the universe into what we see today, dictating where and when stars can form, from the smallest star-forming regions to the grandest galactic structures.
That's a profound thought, that these invisible giants dictate so much. But that leads us to the central puzzle, doesn't it? If these supermassive black holes are so crucial and we see them everywhere today, how did they get so big so fast in the first place? The mystery only deepens when we consider that many have already been found as early as 1 billion years after the Big Bang. That's incredibly early in the universe's timeline. Remember, the universe is what, 13.8 billion years old now?
Right. It's just a tiny fraction of cosmic history.
It implies their formation must have occurred even earlier, during that cosmic dawn, a period when the universe was less than 1 billion years old. How do you get something with a mass of 1 billion suns in just a few hundred million years? It seems to defy the conventional timescales of cosmic growth we think about.
This raises an important question for you, our listener, to ponder. What's the cosmic recipe for these early behemoths? For cosmologists, a crucial clue to understanding their formation mechanism is their number density, essentially. How many exist per unit volume of space at a given time in the early universe?
Okay, so how packed together they were.
Exactly. If we were to find a high number density of these early supermassive black holes, it would strongly suggest they formed relatively frequently and widely. This lends support to theories where they might have originated as remnants of the very first generation of stars, often called population 3 stars.
Those first stars, supposedly huge ones.
Right. Hypothesized to be incredibly massive, hundreds of times the mass of our sun, and very short-lived. They'd collapse directly into black holes when they died. This would provide a widespread seed black hole population from which to grow. You'd have lots of starting points. Conversely, a low density would point to their formation under more special, perhaps rarer conditions, like the direct collapse of massive gas clouds, immense amounts of gas, tens of thousands or even millions of solar masses collapsing due to their own self-gravity without first forming stars.
Skipping the star part entirely.
Exactly. This would create a seed black hole much larger than those from POP3 stars, maybe giving them a head start, but likely under more stringent and less common environmental conditions. You'd need just the right setup. So the observed number density provides a strong hint about which of these pathways was most prevalent in the infant universe, and thus what the earliest chapters of cosmic history really looked like.
So we're talking about objects that are incredibly powerful, but also incredibly distant, shining from billions of light years away and forming in a universe that was a very different place. How do astronomers actually spot these distant, active, supermassive black holes? What's the specific smoking gun that confirms their presence and activity from such immense cosmic distances, especially when the universe itself is still, finding its feet?
Well, when a supermassive black hole is active as a quasar, it shines so brilliantly it can be detected across those immense cosmic distances, like a beacon. The key telltale sign, the definitive proof, is a distinct, broad emission line in its light spectrum.
Okay, the spectrum again. Break that down for us.
Imagine all the light coming from a galaxy, which we can split into its constituent colors, like a rainbow using a prism or spectrograph. Normal galaxies have sharp, narrow spectral lines.
It's like fingerprints for elements.
Exactly, like cosmic barcodes telling us what elements are present and how the galaxy is moving. But in a quasar, there's gas orbiting the central black hole at extremely high velocities, often hundreds or even thousands of kilometers per second, just whipping around. Because of the Doppler effect, you know how a siren changes pitch as it moves past you?
Right.
Gas moving towards us appears slightly bluer, and gas moving away appears slightly redder. With gas swirling rapidly in every direction around the black hole, the light emitted by specific elements like hydrogen gets smeared out or broadened across a range of wavelengths. Instead of appearing as a sharp, narrow spike in the spectrum, it looks like a blurry, wide stripe.
Ah, because the light is coming from gas moving at all sorts of different speeds relative to us.
Precisely. Detecting this broad emission line is the definitive, unambiguous proof of an active supermassive black hole. Without it, you might have a very bright galaxy, maybe lots of star formation, but you can't be certain it's a quasar powered by a black hole. That broadening is key.
Okay, so astronomers knew what to look for, these broad lines. And for years, they've diligently searched for these early quasars, using exactly those techniques. Research groups, including the very team involved in this new study, which utilizes the Subaru Telescope, have made significant contributions. They discovered more than 200 quasars during the cosmic dawn, right?
That's right, over 200 confirmed. An incredible achievement, really, pushing the boundaries of observation.
It really demonstrated these things existed way back then.
Yeah, absolutely. Those discoveries were monumental, showing these massive black holes were around far earlier than many initially thought possible. However, what's fascinating here, and what became a major limiting factor, is that this conventional survey technique, while effective for what it could see, had a significant blind spot.
Ah, okay. So it wasn't telling the whole story.
Not quite. Quasars were primarily identified by detecting the ultraviolet UV light they emit. Because of cosmic redshift, that stretching of light waves as the universe expands.
Yeah, light gets redder over distance.
Exactly. So this UV light from the early universe reaches Earth as visible light, which our telescopes could detect. But the reliance on that original UV light meant we were effectively only seeing part of the picture, perhaps even less than half.
And here's where the real cosmic detective story begins. Because the limitation of those conventional surveys stemmed from a seemingly simple yet cosmically profound issue: dust.
Dust. Simple, everyday dust, just on a cosmic scale.
Exactly. Ultraviolet light is incredibly easily absorbed or scattered by microscopic grains of dust, little bits of carbon and silicates, basically soot and sand scattered throughout galaxies. And many galaxies, especially those undergoing rapid star formation or containing actively feeding quasars, are incredibly rich in this cosmic dust.
They're messy places, essentially.
Right. It's like trying to see a dazzling cosmic lighthouse through an extremely dense interstellar fog. You know the light is there, theoretically, but you just can't see it clearly.
Precisely. This is what we've termed the dust problem. When a quasar resides within such a dusty galaxy, its brilliant UV light, which was our primary observational tool for finding them way back then, well, it's largely absorbed by the dust before it can even begin its journey across billions of light years to reach our telescopes.
So the dust acts like a shield.
A very effective one, yeah. It effectively cloaks the quasar's intense UV emission. This led to a strong suspicion among astronomers for years that the quasars discovered in conventional UV-based surveys represented only a fraction of the true population, like the tip of the iceberg.
We suspected there were more hiding.
Exactly. Many more, we theorized, remained completely hidden from our view, like obscured treasures veiled by cosmic curtains. If we connect this to the bigger picture, it suggests our understanding of the early universe might be drastically incomplete, based on a skewed sample of only the objects we could easily see. To help you visualize this, for you listening, imagine a schematic diagram. Picture a bright quasar at the center of a galaxy. It's blasting out light in all directions. Now, place a thick swirling cloud of cosmic dust around it, like a really dense fog bank.
Okay, got it.
If you tried to see that quasar with UV light, the wavelengths that previous telescopes focused on, it's like shining a regular flashlight into that thick fog.
Not going to see much.
Right. The UV light simply scatters and gets absorbed by the dust particles. It doesn't penetrate. It won't make it out to us across the vastness of space. The quasar would appear incredibly dim or even completely invisible in UV, regardless of how intrinsically bright it truly is. This visual really drives home why we suspected we were missing so many.
That sets the stage perfectly for the persistent curiosity that actually drove this new research we're talking about today. For over a decade, this research team was driven by a hunch. They focused on some of the most luminous galaxies discovered by the Subaru Telescope's Hypersuprime Cam survey, this really powerful camera. These galaxies were initially identified as candidates because they were incredibly bright in certain ways, but without those definitive broad emission lines we discussed, they couldn't be definitively classified as quasars. They looked interesting, but lacked the smoking gun.
Right. They were bright, but the key signature was missing in the light they could previously get.
Yet subtle signs, other hints in the data of a powerful energy source kept the team suspecting that hidden quasars might be lurking within them. They had this feeling that they were seeing the host galaxy, but something brilliant inside was just obscured.
And this suspicion, this decade-long hunch, met its pivotal moment with the launch of the James Webb Space Telescope, or JWST.
Ah, JWST. The game changer.
Absolutely. This advanced observatory was quite literally a game changer. It wasn't just another incremental step forward, it was a massive leap. It provided the necessary tools, the unprecedented observational power to finally test their long-held hypothesis and peer through the cosmic dust veil that had frustrated astronomers for so long. JWST was precisely the instrument they needed to unlock this particular cosmic secret. Its capabilities were almost tailor-made for this problem.
So how did JWST fundamentally overcome this dust problem that had plagued earlier observations? It's not just about having bigger mirrors, although that helps, right? It's about seeing the universe in a completely different kind of light. What was the ingenious solution?
Exactly. The size helps, but the type of light is key. The ingenious solution lies in JWST's ability to observe in the infrared part of the electromagnetic spectrum. For the first time, the team could effectively observe light that was originally emitted as visible light by these distant galaxies.
Okay, wait, visible light. I thought we were talking infrared.
Ah, right. So because of the immense cosmic redshift from the early universe, that stretching of light waves we keep mentioning,
Okay.
the light that started out as visible light way back then, near the quasar, has been stretched so much by the expansion of the universe over billions of years that by the time it reaches Earth, it arrives as infrared light.
Ah, got it. The redshift shifts it down the spectrum.
Precisely. And critically, infrared light, especially longer wavelengths of infrared, can penetrate dust much more effectively than UV or even visible light. It's like the difference between seeing through a foggy window in visible light, where everything's blurry and obscured, versus seeing it with an infrared camera, where the heat signatures can cut through the fog, making it seem almost transparent. So while the brilliant UV light from a dust-shrouded quasar was getting blocked, absorbed by the cosmic dust, the infrared observations allowed them to essentially see through that dust veil, capturing the light that did make it out. This ability to capture faint infrared light from these early obscured quasars, and, critically, to perform spectroscopy on that infrared light to look for those broad emission lines, that was precisely what JWST was designed and built for.
Seeing the redshifted signature.
Exactly. To revisit our schematic diagram, where the UV light was blocked by the dust cloud, the infrared light, which started as visible light near the quasar, simply passes right through, making its journey across the universe unimpeded and reaching JWST's incredibly sensitive detectors. That's the magic.
And this wasn't just JWST flying solo, was it? You mentioned Subaru earlier. This was a brilliant collaborative strategy, a true synergy between two powerful telescopes that maximize their individual strengths. The Subaru Telescope, nestled atop Mauna Kea in Hawaii, with its vast 8.2-meter primary mirror and incredible wide-area survey capabilities provided by HyperSuPrimeCam. It was perfectly suited to cast that huge net across the sky, spotting these rare, luminous galaxy candidates across vast swaths of the early universe. It could find the potential targets.
It's the perfect analogy. Subaru cast that incredibly wide net. Its HyperSuPrimeCam surveys huge areas of the sky, identifying millions upon millions of galaxies, including those few rare potential hotspots that look like they might be hiding these obscured giants. It finds the needles in the cosmic haystack, or at least the potential needles. Then, JWST, with its far greater sensitivity and its powerful infrared capabilities, provides the necessary depth and precision for the targeted follow-up observations. It zeroes in on those specific candidates identified by Subaru, acting like a cosmic magnifying glass, or maybe more like those infrared goggles, to detect the faint infrared signatures and, crucially, hunt for those broad emission lines in the infrared spectrum.
So Subaru finds, JWST confirms.
Basically, yes. As Dr. Yoshiki Matsuoka, who led this study, put it so eloquently, this discovery was only possible with the unique combination of two powerful telescopes. The Subaru Telescope's wide and sensitive survey allowed us to spot rare, luminous galaxies, and JWST was able to catch the faint infrared light from the hidden quasars. He added, "This shows how effective the approach of Discover with Subaru Telescope, Explore with James Webb can be. It truly highlights the power of complementary instruments working together rather than in isolation to reveal a more complete and dynamic picture of the universe. It's a testament to smart scientific collaboration."
So, armed with this powerful Subaru JWST partnership, and with this clear hypothesis about hidden quasars driving them, let's walk through the concrete steps of the actual discovery. This is where the payoff happens. From July 2023 to October 2024, observations were meticulously carried out using the NIR-SPEC spectrograph onboard JWST, that's the near-infrared spectrograph, designed exactly for this kind of work. The team specifically targeted 11 of the most luminous galaxy candidates that Subaru had initially flagged through its wide-area survey, the ones that looked like they could be harboring something powerful but were veiled, lacking that clear UV signature.
And for anyone in the field, the results were truly electrifying. A remarkable 7 out of those 11 targeted galaxies clearly displayed the definitive broad emission lines we discussed earlier.
7 out of 11, that's a pretty high hit rate.
It really is. These were not ambiguous detections. They were the unambiguous telltale sign of an active, supermassive black hole lurking within. This confirmation marked the very first robust discovery of luminous, dust-obscured quasars right back at the cosmic dawn. For years, these objects were theoretical possibilities, nagging suspicion, something inferred but not directly seen this way. Now, they were real, tangible data points in JWST's spectrograph.
Wow.
This raises an important question for you, our listener. What secrets do these newly unveiled behemoths hold about the universe's past, and what else might they tell us about how these early structures came to be?
That's incredible. And for you, our listener, who follows these cosmic discoveries closely, it's worth clarifying how these newly discovered objects stand out. Because we have had previous reports, haven't we, of possible candidates for dust-obscured quasars. But they often remained inconclusive without that definitive broad emission line detection. And JWST has also recently discovered numerous little red dots, many of which do show broad emission lines. So what makes these 7 discoveries so unique and a true game changer compared to those?
That's a great point to clarify, yeah. The crucial difference here lies in their sheer luminosity, their intrinsic brightness. When astronomers talk about little red dots, we're generally referring to smaller, more compact, dust-obscured galaxies with active but typically less luminous black holes at their core. They're interesting, definitely, showing obscured activity, but they're not quite in the same league power-wise as the ultra-bright quasars we previously knew from the early universe, the unobscured ones.
So the little red dots are dimmer, maybe smaller black holes?
Generally, yes, that's the thinking. They represent a different part of the population. In stark contrast, the study has uncovered the first examples of supermassive black holes at the cosmic dawn that are as luminous as the conventional unobscured quasars, the ones we could see easily before, but were simply dimmed and hidden from our view by all that surrounding dust.
So these are the big guns, just hidden.
Exactly. We're not just finding a new class of dimmer, perhaps less influential black holes. We're finding the bright, powerful ones, the real cosmic engines that were completely invisible to previous surveys looking in the U-visible. This means our previous census of the early universe was missing some of the most energetic objects, the ones that were potentially driving significant cosmic evolution, like that feedback we talked about. That's what's truly fascinating here. It's a complete shift in our inventory of the early universe's powerhouses.
Wow, okay, that distinction makes a huge difference. So delving deeper into the spectra from these observations, what specific characteristics did the team uncover about these previously invisible cosmic powerhouses? How powerful were they really? How massive were their central black holes estimated to be? And what did the data tell us about the dust veil itself? How much light was it actually blocking?
Well, the astonishing details revealed by the spectra tell a powerful story of cosmic giants. These newly discovered quasars emit energy equivalent to a staggering few trillion suns.
Trillion, yeah. To put that in perspective, our entire Milky Way galaxy contains maybe a few 100 billion stars. These individual quasars are emitting light equivalent to several entire galaxies worth of stars combined.
This
immense power output.
Unbelievable.
They're powered by central black holes with masses estimated at a few billion suns. Billion with a B.
So truly supermassive.
Oh, yes. And it's important to emphasize that these values, the incredible luminosity and the enormous black hole mass, are directly comparable to the ordinary, unobscured quasars already known from the cosmic dawn. This confirms they are truly massive, truly luminous objects, not a faint or smaller cousin, but full-blown, energetic, supermassive black holes that just happen to be hidden. And crucially, the team was able to quantify the obscuration with remarkable precision using the details in the spectra. Their analysis showed that dust absorbs about 70% of the light that started out as visible light.
Okay, most of the visible light gone.
And a remarkable 99.9% nearly all of the ultraviolet light from these quasars.
99.9%. No wonder we couldn't see them in UV. Exactly. This definitively explains why they eluded previous surveys. It wasn't that these quasars weren't there or weren't bright, it's that the universe itself, with its abundant cosmic dust in these active early galaxies, had drawn a nearly opaque curtain over them, at least for UV light. This empirical measurement of the dust's effect is a key piece of evidence, not just a theoretical assumption anymore.
Okay, so what does this all mean for our understanding of the early universe? This isn't just finding a handful of new objects, exciting as that is. This sounds like it fundamentally changes our cosmic census. What's the big takeaway for you, our discerning listener, about how we should now perceive the cosmic dawn?
Well, the most impactful revelation, the real headline here, comes from reevaluating the number density of these objects, how common they are. By comparing the number of these newly discovered dust-obscured quasars found in this targeted search to the number density of the previously known conventional quasars, the unobscured ones found over decades, the team concluded that these hidden giants are at least as common as the ones we could see before.
At least as common, so potentially even more common.
Potentially, yes. But the minimum implication is that they are roughly equal in number. This is monumental. It means that the total number of bright, highly active quasars, the really luminous ones in the early universe, is at least twice as high as astronomers had previously thought. We were missing half of them, the dusty half. If we connect this to the bigger picture for you, it suggests a far more energetic, more dynamic, and arguably more, developed early cosmos than we ever imagined. It tells us the universe was bustling with these powerful engines, these cosmic architects, shaping their surroundings even earlier and in much greater numbers than our previous observations indicated.
It was a busier place than we thought.
Much busier and much brighter. Just a lot of it was hidden. This has profound implications for understanding the energy budget of the early universe, the speed of reionization, that crucial period when the universe transitioned from being opaque to transparent.
Right, the fog lifting.
Exactly. And the overall timeline of how the first large galaxies assembled. It's like finding out half the major cities on an ancient map were simply hidden by clouds all along. It changes your view of that ancient world significantly.
And bringing the conversation back to that fundamental mystery of black hole formation, we discussed at the very beginning, how do these giants get so big so fast in the first place? How does this doubling of the early bright quasar population influence the theories about how these cosmic titans came to be? Because that's a central debate in astrophysics, right? Which seeds grew into these monsters.
It really is. And this discovery provides critical empirical data, actual observations, to refine and even challenge our theoretical models. We talked earlier about the importance of number density as a clue for formation mechanisms. A significantly higher number density, now confirmed to be at least double what we thought for Brightsate, for bright quasars strongly suggests that these supermassive black holes must have formed relatively frequently and widely across the early universe. It makes it much harder to argue that they only formed under very rare, highly specialized conditions. You need a more common formation channel to explain finding so many.
So it points away from the rare event models.
It leans away from them, yes. This higher density lends stronger support to theories where they might have originated as remnants of first-generation stars, those supermassive population 3 stars we mentioned earlier. Remember, the idea is you have stars hundreds of times the mass of our sun, burning out quickly, collapsing directly into black holes of maybe tens or hundreds of solar masses. If these types of stars were relatively common in the early universe, they would provide a more widespread and frequent seed black hole population. Lots of little seeds ready to grow.
And they'd have time to grow.
Well, they'd still need to accrete matter incredibly rapidly, faster than we normally see today. But having more starting points makes it more plausible to end up with the observed number of billion solar mass black holes within the first billion years. This discovery shifts the probabilities significantly towards such more abundant seed formation mechanisms. Conversely, it provides less support, or at least makes it harder, for scenarios that require more rare, specialized conditions for their formation, like the direct collapse of massive gas clouds into much larger seed black holes of thousands or tens of thousands of solar masses.
Those would give a bigger head start, though.
They would, but if you need a very specific, very rare set of circumstances, maybe pristine gas, no prior star formation, particular halo properties for these larger seeds to form, it becomes much harder to explain such a high number of bright quasars observed so early on. This discovery shifts the probabilities, giving us a clearer direction for future theoretical work and nudging the scientific consensus towards a universe where black hole seeds, perhaps smaller ones from papa stars, were maybe more readily available right from the get-go.
This discovery is clearly just the beginning then. It's like turning the first page of a completely new chapter in our understanding of cosmic history. So what are the next steps for this pioneering research team? What further insights do they hope to uncover from these newly unveiled cosmic behemoths? For you, our listener, this is where the cutting edge of research is heading right now.
The team basically foresees 2 primary directions for future work, both building directly on this groundbreaking find. First, they plan to conduct even more detailed observations of these newly identified obscured quasars. The JWST spectra they've already obtained contain a wealth of information. It's not just about finding the broad emission lines. There are also fainter emission lines from various elements like carbon, oxygen, nitrogen, silicon, and so on. Studying the ratios and shapes of these lines can reveal crucial information about the physical conditions very close to these black holes.
Like what specifically?
Things like the temperature, the density, the chemical composition of the gas swirling in the accretion disk, and the immediate vicinity. It can even tell us about the speed of outflows. This will provide unprecedented detail on their immediate environments and precisely how they're feeding and interacting with their surroundings. And beyond JWST, they also intend to use the Ehime Telescope, that's the Atacama Large Millimeter Submillimeter Array in Chile.
Right. ALMA sees in even longer wavelengths.
Exactly. Almolin is uniquely suited to study the cold gas and dust within the host galaxies of these quasars in much greater detail. While JWST excels at peering through the dust to see the hot gas near the black hole, Ehime can map out the distribution and kinematics, the movement of the very gas and dust that forms the fuel reservoir for these hidden giants. It can tell us about the star formation rates in these galaxies, measure their total gas mass, and see how the black hole's powerful radiation and outflows might be influencing its galactic home on larger scales. This multi-wavelength approach, combining JWST and ALMA, will give us a truly comprehensive picture of these early energetic systems, the engine and the machine it powers. The second primary direction is, well, to find more. The team aims to expand the search.
Cast the net wider.
Exactly. Broaden their hunt for hidden black holes to a wider population of galaxies, including ones that are less luminous than the very bright candidates initially identified by Subaru. The goal here is to fully reveal the complete population of supermassive black holes in the early universe, finding the obscured counterparts to dimmer-known quasars too. Perhaps not just the brightest, most extreme examples that have captured our attention so far. This will give us an even more comprehensive understanding of their cosmic role across the board and really pin down that number density across different luminosities, telling us how common or uncommon black hole seeds of various types truly were right back near the beginning.
And this isn't just planning for the distant future, is it? This work is already in motion. The momentum is there.
That's right. The excitement is high. A new JWST program building on these results has already been approved. Observations for that next phase are scheduled to start early next year. So this ensures continued and rapid progress in unraveling these cosmic mysteries. The scientific community is definitely eager to build on this profound discovery and see what else JWST and other facilities can tell us about this hidden population. #tag outro.
What an incredible deep dive into the early universe today. We've gone from a rather hazy, definitely incomplete understanding to a really profound shift. We've revealed that the cosmic dawn was teeming with at least twice as many bright, active, supermassive black holes than we ever knew, all hidden behind those pervasive cosmic dust veils, just lurking there, unseen. This incredible insight, which fundamentally alters our understanding of cosmic evolution's early chapters, was only made possible by the powerful synergy of telescopes like Subaru, with its wide field view finding the candidates, and JWST, with its unparalleled infrared vision allowing us to finally see through the cosmic fog. It truly makes you appreciate the ingenuity of modern astronomy, doesn't it? And this revelation about hidden quasars makes you wonder, doesn't it? For you listening, if such a significant population of these cosmic powerhouses, these key players, was completely obscured from our view for so long, what other major components of cosmic evolution, what other fundamental processes shaping the universe might still be currently obscured from our view across the vastness of cosmic history?
What technological leaps are needed next to bring those remaining secrets into focus? To pull back those cosmic curtains. It really makes you rethink what seeing the universe truly means and what incredible discoveries might still be waiting for us, just beyond the veil of what our current instruments allow us to perceive.